Je ne parle pas en français, je parle en anglais. It's going to take less time if I speak. Okay, some of the discussion just now has just raised lots of the points I was going to mention very briefly, so I'll just reinforce them as I go on. So I came to Despar in 1985. That's a long time ago. I found 3 photographs. So one is like this. Now this is snow, so I couldn't work out if this was 85 or 86. The internet said that January 85, you see the grey bars are the minimum and maximum during the day. So there was a day in January where it didn't get above -10. And I do remember that January being, I arrived in Paris and it was the coldest I'd ever had. Okay, right, so that's how I think. Okay, but this is, but again, from the period, just to show you that there were some sunny days. So I came to Despar on an exchange. It was a 2-year exchange from the Royal Society in England. And one of the reasons I came to Despar was actually because of Marc Leroy. And so there would be papers which he was publishing. He was in the States, and he was publishing these really seminal papers about simulation of shock waves, and using a particular technique called the hybrid simulation, which allowed the simulation to follow the ion motion of the protons, essentially, in the solar wind. And so there were lots of these lovely pictures full of dots. Each dot. Sorry, where's my cursor? Okay, so there were all these plots in the old days with lots of little tiny dots. Each dot was a particle within the simulation. Now, but as you see, that so Marc Leroy, or Leroy, because he was always in the States, said, now at Despar, Observatory de Meudon. So in 1983, I sort of started speaking to him, and I visited him, and he said, well, actually, I'm going to leave Despar. I'm going to leave space plasma completely. And in fact, so I arrived and he had left, and I actually worked with his last publication, which was his thèse, but not his normal thèse. It was the Doctorat en Sciences. So this was his sort of final work, but this had everything that in it. In fact, another reason that there was a connection with Despar was that my supervisor, Steve Schwartz, who many of you will know, he had actually worked with Bernard Leroy in the early 1980s, and so he actually already knew the group at Despar. Now, it's very nice that Andre brought up these papers by Scudder. These were called the Scudder papers, and so this was 1986 they were published, but they were talked about in the community from about 1984, 1983, that people knew that there was this grand opus of in the end, there were 3 linked papers. And they were all Scudder papers, but it was when I arrived here that I realized actually that a lot of the work was being done here by Andre, and in particular by Catherine, and it's kind of sometimes forgotten the author list. So as the idea of these papers was to take one single shock crossing and really pull it apart, as Andre said, with 10 instruments, and this is the same plot that Andre had of this single shock in November the 7th, 1977. Looking back at that paper now, it really has all of the elements of modern shock physics, but it also has some of the problems of modern shock physics, which is overload of information. So there was this lovely pull-out in the paper where you could pull out and see essentially every single particle distribution measured by the instruments for both the electrons and the ions passing through the shock. And even at the time, I doubt that anybody got any useful information from this plot. You know, this is simply overload. I'm going to try and take just 2 or 3 points from that work from the period 84-85 when Catherine when I interacted with Catherine, and sort of mention some things from then and try and bring them up to date. So one of the main points about this paper was to really solidify that you could do what is now taken for granted with shock physics, which is that you can take a time series, so that's a series of observations that, as time progresses, and convert it into distance. Now, what this means is, and Olga mentioned it, of saying that if you can say that a structure is moving through the plasma with a certain speed, if you have a measurement at one point, you can convert that speed to distance. Now, why is this important? Because obviously in physics, we deal with the importance of characteristic distances. In our plasma, we have a characteristic distance, which is the gyration or the rotation of a particle. We have other characteristic distances associated with dissipation. So physicists are always really interested in absolute distances. So the idea was to take this shock and convert from time to distance. And so this is why you need to have, as it says here in this little thing at the top left, a determination of the load of the shock geometry. Essentially, how is the shock oriented? Because you only had 2 spacecraft, so you need to have the orientation of the shock. So there are parameters of the transition because it's a shock wave, so you can look at the shock conservation relations across it, linking the speed, the density, magnetic field upstream and downstream. The shock structure, so actually what shape the shock is, and Andre has mentioned that. But as it says there, converting temporal observations into a spatial profile. And so really one of the key things here was, if you notice that this is the same profile, but now plotted in distance units. These are, it doesn't particularly matter what they are, it's a convected gyro radius. It's the distance which interests plasma physicists. But the point is that this is plotting in terms of distance. And why is this interesting? Because you can then take a model of a shock where we've got these physical distances and compare it with the observations. So this is the schematic model of the observations. And from these observations, you can kind of see that there is this, there's a region here which is called the foot. That's kind of corresponds to this little pedestal of foot here. There's an overshoot where the field is higher and then it goes lower on the downstream. And there might be a region here which is called an undershoot. Well, maybe this is the undershoot here. But you can see already with these observations, it's very noisy or turbulent. Of course, that nowadays we're more interested in that than the basic structure. Now, I came with a background of wanting to do simulations and theory, but in Despard, when I was surrounded by observations, and we had these lovely pieces of paper from the IC experiment, in particular, it was called the Sounder experiment, but it also had essentially it measured the electric field between a frequency of about close to 0 and 25 kilohertz, which are essentially radio frequencies. Oh, sorry, 25 to 50. Sorry, 50 kilohertz. And I wanted to pull up this paper again, which was mentioned. And so Catherine was working on this while I was here. And essentially, it was looking at this so-called 2FP radiation produced in the foreshock of the Earth's bow shock. And we've had some discussion about what that means. So these are radio waves generated by the plasma. And so it's a process that can happen in many other places in the universe. But we've got the spacecraft close, right in that plasma, so we can make the observations. and the FP line is called the plasma frequency, and it's one of the characteristic frequencies of the plasma, and it's very closely linked to the density of the plasma. And so you see here that there's this black line where there is some radio energy at, or electrostatic energy, electric field energy at around 20 kilohertz. That corresponds to the plasma frequency and tells us what the density, the electron density of the plasma is. This more diffuse sort of emission up here, this black line here is the 2FP, it's twice this. Right, so Catherine did this marvelous, really lovely piece of work, very detailed, not only just saying what are the observations, but making a model, including many effects, including the emissivity of the emission, the directivity, the possibility of scattering of the radio waves in the plasma. And really, this is, people mentioned the precision and the amount of work she did, and this was just really nice. And so even built into this, there was a little piece where they noticed that sometimes this 2FP emission line is actually split, bifurcated. And so it seems that the solar wind has two plasma densities, which produces two 2FP lines. And that by saying that you could have a discontinuity in the density, you can actually make a prediction about a rough estimate of the size of the emission region, which is about 60 RE, the Earth's radius, that it's generated on this magnetic field line, which is tangent to the bow shock, essentially where the electron foreshock is, which we've seen in the pictures already today. So it's a really nice piece of work. I don't think it's been surpassed. This is the ADS entry in the bibliographic database. So this is 1988. This was produced by Analysis Geophysicae now, which is unavailable. So this paper has been lost digitally. No sources found. So I've got a paper version of the reprint. If anybody wants it. Not only that, this abstract is not the abstract in the paper. I don't actually know where this abstract has come from. It seems that they have sort of produced an abstract of an abstract. Okay. But this paper for me is an epitome of Olga has mentioned the careful work that she saw Catherine doing later on with the Whistler survey and so on. But for me, this is also epitomizes the way that Catherine worked as a scientist. Every possibility, most people would say, just as a mention, well, maybe these radio waves are scattered by density fluctuations. No, what was done here is they did a full model, including the effects of scattering, just to see what it would do. Okay, so thank you, Olga. You already mentioned this paper. So being surrounded by data, for some reason, I started spending time just looking at these pages and pages of data. And sometimes things would just pop out at you. And this was one example where there was in the solar wind, essentially you can see that these dark lines are this 1FP, the plasma line. And there was this rather strange little period here where the local density had gone down, but it seemed that it was producing emission at the density it used to be. So this is where the density had changed abruptly. And so we managed to get this into Nature. These were the days when Nature was becoming just a letters. It tried to be a letters journal. Nowadays it's become very high class. But this, looking back, I'm very proud now of the co-authors on this paper. This then kind of linked to another activity which I've continued to study for the kind of many years after that, which was if we can produce the FP radiation in the electron foreshock, we have to explain the electron foreshock. In other words, we have to explain why are electrons accelerated at the shock and then travel out into the foreshock in the solar wind, which then generate electrostatic plasma line, and then the 2FP radio. Now, there's another link to the work of Madon. This was now that the other Marc Leroy, working with Andre, who put forward a theory of electron acceleration by magnetic mirroring from the shock, and C.S. Wu in the States produced something in the same year. This paper also, unfortunately, Andre, has been digitally lost. Okay, I'm not sure how we can change this. But essentially, this kind of work has been a thread through the many years since then, and in particular studying magnetic mirroring of electrons in shock waves using simulation. So this is linking the work I was doing with the hybrid simulation from Marc Leroy and the electron foreshock and the observational work. So this is some recent work that has been done with Domenico Tronto, at the time of my PhD student. And essentially what we were doing was three-dimensional simulations of a shock wave. And when you do simulations of a shock wave, you find that at high Mach number, the shock wave is not just a steady structure, but it is covered in, let's call them ripples, small waves, fluctuations. So on the left here, we've got a shock wave at low Mach number, and at low Mach number, everything is pretty steady. Everything is smooth and we would say laminar. So this is the dark blue is the upstream. This is the downstream. So it shows the compression in the magnetic field from upstream to downstream. We get the increase across the shock, and this plane is the YZ plane. So it's now taking this red dashed line and looking at that shock plane. So it's what's happening at the shock across the two-dimensional plane. And you can see that everything is pretty steady and there's not much variation. If you go into a higher Mach number, do the same thing now, the shock is not a single value, but it's actually changes in value by quite a large amount. You see that this change here is from 1 to 7. What does that mean in terms of the actual shock structure, shock parameters? Well, Olga mentioned this angle between the upstream magnetic field and the shock normal. So that's a way of sort of saying, well, if we've got a shock propagating in this direction and we have a magnetic field, this angle tells us how they are oriented relative to each other. And what we find when we take the low Mach number, the difference in that angle, the theta Bn, so the difference produced by the fluctuations is very small, as we'd expect, because we don't see much variation. But if we go to the higher Mach number, the variation in that angle, as we move across the shock, is actually really large. So this is this scale here is plus or minus 50 degrees. And so the sigma, the standard deviation is plus or minus 15 degrees. So even if you believe the simulations, if you take a shock, the Scudder picture of saying what is the best fit to the parameters is actually inherently a rather difficult question, because these simulations say that inherently that theta Bn, that angle about the parameters of the shock, is actually plus or minus 15 degrees. This isn't noise. This is actually the shock itself. Anyway, so this can also affect the theories of magnetic reflection, and because it introduces scattering into those theories. And so these fluctuations actually produce a sort of acceleration where you can look at the acceleration of, so this is starting, these are the accelerated electrons at that shock for different Mach numbers. And as you go to higher Mach numbers, you essentially see larger acceleration, larger energies. This is going up to, say around 10 kV. And so essentially that as you make the transition from the laminar shock to the more turbulent high Mach number shock, you start producing these electrons, and these are the electrons that would then go into the electron foreshock and produce the radio emissions I showed. This is just a representation of what that shock looks like now in 3 dimensions, and you see that this is the these structures, which are places where the magnetic field is stronger. These can actually change the orbits of the electrons and scatter them. And it's that combination of the mirroring and the scattering which produces this acceleration. Right, how am I doing, Olga?
It's okay, we have 7 minutes.
50 minutes left?
Yes.
10, actually 10.
Oh, okay. If I ask again, will you promise me it's still 10? Okay. Okay. Going back to this figure, because Andre didn't mention it, but there's this rather strange double line here with this RD. Okay, so I remember at the time, that Catherine was working on this, and she said, "Oh no." Again, I'm not quoting, but she had said, "Oh no, look, I've just discovered that there's a rotational discontinuity just in front of the shock that I've been studying for weeks or months, and that I'm going to have to do everything again." So what it was is that just here, you can see that there's a little change in this component of the magnetic field. So what's happened is the magnetic field has just changed a little bit before the shock crossing. Now, nowadays, we shouldn't be surprised by that. The solar wind is full of turbulence, and it's also full of these discontinuities. So the magnetic field in the solar wind is always changing around a little bit, but sometimes it changes quite a bit in a short time. And that's what we call it, a solar wind discontinuity, magnetic field discontinuity. And so one of these had happened just before that shock crossing. And it, of course, if you wanted to calculate what was upstream and what was downstream, you would get this upstream is actually different from this upstream. So your upstream now is no longer a big, strong period, but it's actually a really small period just before you see the shock. Now, why is that interesting? Because it turns out that interactions between these discontinuities and shock waves is actually a really big thing. It's not unusual at all. So in 1989, we were trying to explain events which are known as hot flow anomalies, active current sheets. They have many other names. Olga showed some of the pictures or Andre showed some of the pictures in the quasi-parallel shock of these different phenomena. And these are all related to these kinds of events. Essentially showing that if you had one of these discontinuities hitting a shock where you could find some of these reflected ions, you could in fact get these reflected ions would sort of weave their way into the upstream region along the discontinuity, simply because of the magnetic field is different on the two sides of the discontinuity. So instead of the ions just going all one way, they would suddenly see a magnetic field which took them in the opposite direction. And I'm just putting this figure, this was a figure in the paper. You could say those are the days where you could have cartoons like this. This is marvelously naive. So why is this still an issue? The interaction between discontinuities and shocks, because you see them all the time. This is a paper using PSP, Parker Solar Probe data. This was led by Joe Giacalone. And basically, so this is a shock wave seen in the solar wind. The blue is the total field which jumps up. And you can see that the red is one component. So the red component changes. So that's okay. So that shows you that you've got a shock. But you can see that about 10 minutes or so later, the red component actually switches and changes again, and the green component changes. So no, this is downstream. So downstream, we're seeing a change in direction. Now, in an interplanetary shock, the shock is propagating through the solar wind. So everything that was in the solar wind is eaten up by the interplanetary shock. So this discontinuity, which we see downstream now, at earlier times was upstream. Now, why is this event interesting? Because if we look at the flux in the energetic particles, these are particles between 100 and, let's say, around 500 keV, they actually go down in intensity just behind the shock. This is not expected at all. We expect a shock to accelerate particles, and then downstream of the shock, they should have roughly the same intensity. I mean, it's downstream, nothing else is happening. But what has happened in the past is that there has been a discontinuity which has been eaten up by that shock wave. And you can sort of see, I'm going to have to speed up a little bit. So if I plot it, so this is the same shock. If I plotted this angle, theta bn, the shock normal angle, when we see the shock, that shock normal angle is around 50 or so, 50 to 60. But if I go downstream into the region where we see this change, the downstream discontinuity, that theta bn is around 90. So what we've had is a shock wave that has changed its angle. It's the shock normal angle. I'm going to skip over this. We saw a similar event with cluster and published it earlier on, but the Parker event is interesting because what Joe Giacalone did is that he did a very rough model of the particles at the shock, saying that essentially we've got this discontinuity which is interacting with the shock. So this is on the left is the upstream, on the right is the downstream. This gray region is this, we call it a flux rope-like structure. We're not sure if it is a flux rope, but it's a structure where the magnetic field is different for a short period of time. And if you put some particles into that magnetic field model and let them scatter and let them accelerate, let them interact with the magnetic field, you find a picture which looks like this. Essentially, in this structure, there is simply the number of accelerated particles is reduced. So if we plot what the profile looks like, we actually see this increase beforehand and then a decrease. So this pattern is completely related to the discontinuity that we see in the solar wind being eaten up by the bow shock, being eaten up by the interplanetary shock. You can do the same thing looking at the time series. This is the top is the observations, and the bottom is this model where you can see the same dip in these in what we would call the lower energy. So there's between 100 and kV and about an MeV. So so that idea of, back in the day, 1977, looking at that rotational discontinuity. Nowadays, we would actually say, what's the effect of that rotational discontinuity? Now, finally, I'm just trying to wrap up. I'll try and do this quite quickly. The other thing that was really interesting in the Scudder paper was this idea of saying that I want to go from a temporal profile in time essentially into space. So for that, I need to have a steady structure which moves at a roughly constant velocity over the spacecraft. And then I can say that whatever the time is, I can say what the distance is, because I've got a velocity to convert between the two. Now, this is one of my favorite shocks. This is a shock which was observed at the Earth's bow shock with cluster. This is a special shock because it has a very, very high Mach number. So this is a high alphane Mach number. So that's the ratio of the flow speed to the alphane speed, which is related to the magnetic wave. It also has a very high plasma beta. The plasma beta is the ratio of the thermal pressure to the magnetic field pressure. So that's also very large. So the reason why it's a high alphane Mach number is because the magnetic field is very low, which also makes the plasma beta very high. So this is an enormously large Mach number, but actually, if you calculate the Mach number with the sound speed, this is very, it's not very fast. It's only 5 or 6. But why is this interesting? The shock crossing I showed you before, the Scudder shock crossing, that all happened in tens of seconds. The time scale here now is in hours and minutes. So this is so if we say the shock crossing is around here, this is at around 1 hour 1:56, and it carries on till 2:18. So that's 20 minutes. So this is 20 minutes where we see the shock, or part of the shock, or the shock doing something. We can decide what that is after a while. But this is a long time. Okay, if the solar wind moves at a speed, we've got that speed here. It's around 300 kilometers per second. Okay, so if you think about how much solar wind has moved in 20 minutes, what size of solar wind that is in 20 minutes at 300 kilometers per second, that's a really large distance. But we're seeing this shock and little bits of it. So these little bursts, and this is the magnetic field. But we know that actually, even here, it gets small. These little bursts get smaller and smaller, very difficult to see. But if we look in the reflected particles, that's in this blue line. So it's the temperature anisotropy, which is a signature of the reflected particles. We can see they keep going up to this time over here, even though the magnetic field is really small. Although if you look at here, you can see very, very small little pulses. So what is actually happening here? Is this space or is this time? Because the way that we interpret this is actually that the shock is almost stationary and that we are passing through it very, very slowly. In fact, probably at the speed that the spacecraft is traveling, which is only about 1 to 2 kilometers per second. So this whole 20 minutes is the same as the 10, 15 seconds in that other shock. But for that other shock, the shock was moving at 20 or 50 kilometers per second. Yes?
So is this quasi-parallel or quasi-perpendicular?
This is quasi-perpendicular. This is an 85 degrees. This is 85 degree shock. Okay. So these are fascinating shocks. By the way, again, going back all the way to the 70s and so on, people had classified the bow shock into a high beta regime, which they called sort of turbulent shock or a non-stationary, non-steady shock. And that's kind of been forgotten, that the very high beta shock was classified like that. So people who are interested in the history, that this fits into that idea. Right, why is this interesting? Because people have gone to Cassini to say what happens to very high Mach number shocks. And actually, you see the same shocks at Cassini. So this is at Saturn. By Saturn, the magnetic field of the solar wind is reduced, and so you kind of tend to get these very large alphane Mach number shocks. And what was done was that these little pulses, you see, they're very regular. And it turns out that they've all got roughly the same period. So when you look at many of these shocks, which you can see at Cassini, that period of each pulse is about 1/3 of the iron cyclotron time. So that's the time that it takes for a proton to do one complete circle in the magnetic field. And so, this is telling you that it's something to do maybe with these particles which are reflected and gyrating. They've all got the same period. So it looks like the Cassini bow shocks. you actually see a gradual increase. So when you enlarge the magnetic field and the density, you see these pulses, but the pulses are on top of a steady increase like the foot, and you have this very long foot. What's happened here? This is weird. Sorry about this. What's happened? No, I seem to have lost a picture. Okay, never mind about that. Okay, I made the talk shorter. I'm going to list this out. Okay, presumably I've got minus. Okay. So this I wanted to just sort of try and wrap back to what was being done early on with shocks, because what we're probably looking at here is not the spatial profile at all of the shock, but actually a shock which is has within it a time scale which repeats. So you've got this sort of oscillating period or a repeating period, and that's what we're seeing, which is a period of around 10, 15 seconds. So what is better, space or time? Now this brings us to a question of what is actually controlling the speed at which we see a shock. I mentioned that that shock, the scutter shock, the shock was actually moving. It probably moved because of the rotational discontinuity. The rotational discontinuity would have changed the theta Bn, which, because it changes the physics and the shock conservation relations, actually changes the shock speed. So that rotational discontinuity wasn't just an accident. That was why the shock was seen. Now, why, for these shocks with the pulsations, do we not see that motion? Well, the fact is they're very, very large beta. That means that they are dominated by the gas pressure. So they're essentially a gas dynamic shock. And for those shocks, the magnetic field angle isn't so important. So the magnetic field angle can flop around and the shock speed doesn't change. So it's actually very, very steady. So we've actually got a selection effect. For a high beta shock, the shock is more gas dynamic, and therefore it's a very steady bow shock. And that means that you can see anything which happens with a long period within it. If you've got another kind of shock, which is the standard, more typical plasma beta, the shock will move rapidly over the spacecraft, and you will never see any periodic variations at periods more than a few seconds. So we've actually got an inherent selection bias in this whole idea of studying shocks at the bow shock and elsewhere. Okay, I just wanted to finish by saying that there was a connection between DESPAR and Queen Mary through Steve Schwartz. And Steve and I were doing some work during my PhD of looking at some field-aligned beams in the shocks just upstream of the shock. And Steve had obviously contacted Catherine to ask about the data. Now, the only reason I found this is that I'm sort of semi-retired and I have to clean my office. So I'm actually finding some of these things that you call archives, or old rubbish. And so this was a letter that Catherine wrote to Steve Schwartz saying, this is the data. And so she sent some printouts of data. But I just wanted to finish with what she says at the end. Okay, so that was typical of Catherine, to do all the hard work and then to finish it with this, just such a nice, pleasant way of rounding things off. And so I'll just finish up. That was my final poem.
How old were you there?
It looks about 13, isn't it?
Yeah. and this is Marc Leroy?
So this is George. If I'd had time, I would have spoken about Jack. Yeah. I'd have spoken about his work as well, which is also coming around here.
Il y a des questions. Do you have questions?
Oh no, okay.
Yeah.
Yeah.
Can I? The shot you showed is
This one.
yeah, the very intriguing
sorry,
one.
I
The
don't
very
know.
intriguing one. Have you an idea of about the variation in the solar wind of the conditions in the solar wind during this?
Yeah. So
During this 20.
So this is very steady. So we look for these shocks by looking for very steady solar wind conditions. Because of course, you need, even you want to have a high beta for long enough that, you know, for this 20 minutes, half an hour. So you need to look for dynamic pressure, which are constant for, you know, half an hour or so. So that was done on purpose. So we found about, so in this paper, I think there are 3 such shocks clusters.
You could not use a cluster to get an idea of this.
So one of the issues is saying that, well first of all, is knowing how to find which particular ramp because of course this is now, you know, the models that you have. You know, I don't want to push them forward. You know, so we know that if you so by the way, this is exceptional. This magnetic field goes up to 40, and the upstream magnetic field is sort of, you know, 0.5 or something, 0.1 or something. So in terms of compression, you'd say this was impossible. Okay. But if you look at the average compression across the shock, it matches the high Mach number ratio 4 prediction. If you average, you know, over 5-10 minutes.
That's a good question. What the data on the other spacecraft look like?
Cassini spacecraft. So
this is cluster. So this is C1.
Yeah. So we tried to do that for the, we were looking at that for in particular. So each of these little pulses is actually a wave packet. And so we were looking at that for the time differences between them. They're quite close together for this. So it sees essentially a very similar picture.
Very brief remark. Indeed, in preparing my talk from this afternoon, I noticed the absence of source for the MLS Geophysique paper that you mentioned. I think that if you have the reprint, it's very possible to send some scan to ADS and they fix it. And it's quite important, I guess.
So I was actually going to ask that.
There were some people at the observatory being concerned by that, but I think it's possible to contact it.
Yeah, because ADS does have some internal sources. Yes. It was actually, I only thought about that while I was doing this talk.
Because it would be very useful to have this online.
Please don't leave the, I mean, there are maybe people who want to escape, but we will have now the group photo, and then we have lunch here. Il y a le buffet qui va être servi. Donc, on va faire une photo de groupe. Je ne sais pas, est-ce que vous pensez c'est à la sortie de... Oh, thank you very much, David.